All right. Angular momentum. Okay, angular momentum, sometimes there's collisions that involve rotation. You're actually going to see one example here. Okay. Momentum is a quantity that's conserved. So if there's no external forces that act on the system, we've always said that linear momentum is conserved. Angular momentum is conserved, okay, if there are no external torques. Torques acting. Okay, so if there's no external torques acting, then angular momentum is conserved. Okay, we must take it about some point P in space. Okay, angular momentum depends on the point chosen, but regardless of the point, angular momentum is always conserved about that point, no matter where that point is or where you decide to move it. Okay, if you have a solid object that is going to rotate about its axis, okay, angular momentum is simply L equals I omega. Okay. However, if it's like a point mass traveling with speed v about some point p, okay, then the angular momentum is simply equal to r cross p. Okay, and that is the same as r cross p, which is linear momentum. Okay, and then we can also write that as mvr sine theta. Okay, or mvr perpendicular. Okay, and you see that right here. R perpendicular is simply r sine theta. That's where the sine theta comes from right there. Okay. Okay, you did this lab. It's the circular motion lab. A student uses the apparatus shown to whirl a bob of mass m on the string, an end of a string, in a circle of radius r with angular velocity omega naught. Determine the following. Okay, moment of inertia of the bob. Well, all all atoms of the bob are same distance from the axis of rotation. Okay, so we can say that that's I equals mr squared. Okay, that's just our basic moment of inertia equation. Okay, to get the angular momentum of the bob, all we got to do is take L equals I omega. Okay, and just plug in my I value, mr squared. Okay, times omega naught. Okay, sorry, this should be L naught. Okay. To get the kinetic energy of the bob, okay, it's got to have rotational and translational. Okay, so for rotational, that's 1/2 I omega squared. Okay, and that's going to give me 1/2 mr squared times omega naught squared. Okay, that's all you have to write for that. And then the translational kinetic energy is 1/2 mv squared, which is going to be 1/2 m omega naught times r squared. Okay. So that's how you get that. Okay. Okay. The If you pull on the string and you decrease the radius, then the angular momentum should remain constant because what's going to happen is the tension force. Okay. Tension force. Okay, is directed towards the axis. Okay, so there's no torque applied as a result. Okay. Okay, so now let's determine the new moment of inertia. Okay. All we have to do here, okay, is recognize moment of inertia is equal to mr squared. Okay. Well, the radius is now 1/3 of what it was. Okay. You have to square the 1/3 as well. Okay. So that means that my moment of inertia should change by 1/9. Okay. What about the kinetic energy? Well, um, K naught is equal to 1/2 mr squared times omega squared. Okay. Okay. But just as an aside, okay, just as something off to the side here, angular momentum has to be conserved. Okay. So what's happening here is that if my moment of inertia is changing by 1/9 and the L should stay constant, then omega has to change by a factor of 9, okay, to compensate. So that means that this is actually 9 times omega, okay? And then what would have to happen is the kinetic energy, oh sorry, and the radius is 1/3. Okay, so then when you square this gives you 1/9. This gives you 81. 81 over 9 is just going to give you 9. So this is going to be times 1/9 times 81, and then it ends up being that the new kinetic energy, okay, is equal to 9 times what the kinetic energy was initially. Okay. Okay. Okay, let's take a look at this one. This is a little. There's a little merry-go-round or a little, um, shoot, a little like yeah, I guess you could call it a merry-go-round, right? I can't think of another name for it. And the problem involves me. Okay. Um, the okay. So the mass is 60 kilograms. So a person of mass 60, it's me, mass 60 kilograms is running towards a merry-go-round at a speed of v equals 2 meters per second. The mass of the merry-go-round is 200 kilograms. The radius is 1.5 meters, and moment of inertia is 1/2 mr squared. Merry-go-round can freely rotate, but is initially at rest. Okay, and okay. I don't know. Sorry, I saw something I needed to look at. It's initially at rest. It can freely rotate. Okay. Mr. Mitchell jumps onto the edge of the merry-go-round, holds on, causing merry-go-round to rotate with angular speed omega, and this experience will lead him to teach physics. Which here I am, right? Okay. So now we need to figure out the value of omega. Is the first part. Okay. Well, what's happening is I'm running into the merry-go-round. Okay, a distance r from the center. Okay, and then what's going to happen is I'm going to it's going to rotate this way. So to find the value of omega, all I need to do is recognize that angular momentum is conserved in this case. Okay. So my initial momentum is technically I'm just moving about this point P. Okay, this is like my point P right here in the center. I'm technically moving linearly about that point. So this becomes mvr, okay, equals I omega. Okay. I only have to do r because that's the perpendicular component to my velocity. Okay. Well, I need to figure out the moment of inertia. Okay. This is going to be the moment of inertia of the kid. Okay. Plus um, the moment of inertia I'm going to call this the MGR, the merry-go-round. Okay. Well, the kid moment of inertia is just going to be mr squared because he's a point mass rotating about an axis, and then the merry-go-round is going to be 1/2 capital MR squared. Okay, so I'm just going to calculate all that stuff. This is the mass of the kid, mass of the merry-go-round. Okay, this is going to be 60 times 1.5 squared. Okay, plus 1/2 200 1.5 squared. Okay. And then I is going to be equal to 360 kilograms times meters squared. Okay. Okay. So when you calculate all that out, you end up getting 360. Okay. Okay. Mass ends up being 60. The velocity we got is 2. This is all stuff that's just coming straight from the problem. Okay. I already got I is 360, so I don't need to recalculate that unless I really wanted to. And then omega, we don't know what it is. Okay. So we're gonna figure that out. Okay. Okay. And so all I got to do now is multiply everything together. Okay. So this gives me omega equals 60 times 2 times 1.5 all over 360. Okay. And then you calculate that out, and I end up getting omega equals 0.5, sorry, not meters per second, rad per second. Okay. Okay. Kinetic energy lost during the collision. So yes, when I impacted with the merry-go-round, there was kinetic energy that was lost. It's pretty easy to figure out though. You just need to do the initial kinetic energy, which is translational. okay? And then do the final kinetic energy, which is rotational, okay? For both people, okay? So the initial kinetic energy is going to be 1/2 mv squared, okay? And that's just going to be 1/2. The mass is just Mr. Mitchell because only Mr. Mitchell is translating, okay? 60. And then the velocity is 2 squared equals 120 joules, okay? The final kinetic energy, which is all rotational, is going to be 1/2 the total moment of inertia of both the system, final omega. Okay, so I calculate this out: 1/2 360. The rotational is 0.5 squared. Okay, and then when you calculate this out, this ends up being 45 joules. Okay, so you see that there's a pretty big discrepancy here. We lost 75 joules in collision. Okay. Okay. Now here's something important to note. Okay. Here's some fun stuff to note. Okay. The angular velocity, acceleration, and angular momentum of an object are all actually vectors, okay? And the directions are perpendicular to the circle about which the object rotates, which is kind of weird to think about, but if you think about maybe like a bike wheel, if you have the bike wheel with the handles and you spin it and you try and rotate it, you can actually kind of feel the momentum, okay? L and omega are determined by the right hand rule. If you curl your fingers in the axis of rotation, then your thumb points in the direction of L and omega, and you did that in magnetism, okay, with the right hand rule. It's no different right here, okay? All right. This example right here is a collision involving rotation, not like a ton of rotation, but a good amount of rotation. Okay. What it is you have two carts. One of them has a rod on top, has a bar on top that can be hit and it'll rotate. In the first case, okay, both carts are set on the same track, and one hits the other. Okay. And then the bottom cart ends up at rest. So how fast does a top cart move out of the collision? You just have to do conservation of momentum. Okay, m1 v naught equals m2 plus the mass of the bar v final, because this is a system with the mass 2 and then the bar. Okay, if I then plug everything in, m1, okay, is 10, the v naught is 20, m2 is 25, the bar's mass is 75, so it's a total of 100, and then v final. Okay, so this ends up being 200 equals 100 v final, and you don't have to be a rocket scientist to know that v final is going to have to end up being 2 meters per second. Okay. Angular velocity of the rod after the collision. Well, guess what? Take a look at it. There is no torque being applied to the rod as a result of the collision. So nothing changes. It's going to go 0. Okay? 0 because no angular momentum about rod's axis. Okay, there's no angular momentum about the rod's axis because they both exist in you see that, right? There's no angular momentum because there's no perpendicular component, okay, to the axis. And then how much kinetic energy is lost during the collision? Well, that's pretty easy to solve. You just do initial KE, okay? Initial KE and then final KE, okay? The initial kinetic energy is just 1/2 mv squared, so 10, 20 squared. You end up getting 2,000 joules. Okay. The final kinetic energy is 1/2. M is 100. V is 2 squared, and you get 200 joules. So we lost 1,800 joules in the collision. Okay. So we lost a lot of energy in that collision. Okay. In case 2, now both the carts are on different tracks. The cart with the no bar moves towards the other with this initial speed. It strikes the very end of the bar. After the collision, the bottom cart's at rest. Okay. Well, how fast does the top cart move after the collision? It's actually going to be the exact same. Okay. Same as above. Okay. Because your linear momentum is not changing. Okay. So V final would be equal to 2 meters per second. Okay. Okay, angular velocity, okay, um, is, again, we can figure this out with conservation of momentum because we are going from translational momentum to angular, okay? So I'm going to do m1 v naught r, or sorry, I'm taking my angular momentum, conservation angular momentum, okay, equals I of the rod, okay, omega. All right. So then I'm just going to calculate everything out. I need to figure out what the inertia of the rod is, okay? Well, the inertia of the rod, this is a rod pivot about the center, so it's 1 over 12 ml squared, and that's going to give me 1 over 12 parentheses 75 times 2 squared, and I end up getting 25 kilograms times meters squared. So then I'm going to plug all that stuff in. 10, 20. The radius is 1 because it's 1 meter. It's a 2 meter long rod pivoted about the center. So then there's 1 meter right here. Okay. Um, Moment of inertia of the rod is 25. Omega is we don't know yet. That's what we're trying to figure out. Okay. 20 times 10 is 200 divided by 75, or sorry, 25. You end up getting that omega is equal to 8 rad per second. Okay? 8 radians per second. Okay? How much kinetic energy is lost during the collision? That's a good question. Okay? Before, okay, it's the same, okay, as above, because nothing really changes about the beginning part. But the second part now, there is translational and rotational. Okay, so we would have after we would have 1/2 mv squared plus 1/2 I omega squared. Okay, and then we would do 1/2. The mass is 100. V is 2. Okay, and then we have to add 1/2. The inertia is 25. Okay, and then omega is 8 squared. Okay, and then we calculate the whole thing out and we end up getting 1000 joules. Okay, so we ended up actually in this case only losing 1000 joules this time. Okay, all right, that's angular momentum. Okay, all right, we'll be back with the next one.